From as long ago as 2600 BC, gears have established an illustrious history spanning almost 5,000 years. From the south-pointing chariot of ancient China to the chariots of fire of today, gears have been there. From the delicate works of a fine watch to the enormous gearboxes of industry, gears are there. Gears are generally not visible, frequently functioning out of sight, deep within a machine, or hidden in an unimpressive gear case, and for this reason, they're easily overlooked and often ignored. Without gears and gearing, life as we know it would not exist. There would be no automobiles, and industry would be in its most primitive state. Gears represent a hidden asset that should never be taken for granted, because they perform critical functions. Transmitting power, changing shaft speed, changing rotational direction or torque, redirecting motion, and splitting a power source to drive several machine elements. The function to be performed determines the selection of the type and size of the gears to be used. A brief review of some historical points on gears, and a discussion of some of the terms used in gear design and application will provide a useful insight into how gears work and why the differences between gear types and configurations are significant. This will form the basis for later discussion of the importance of proper gear lubrication. Any discussion of the different types of gears and their applications must begin with a review of some of the basic facts about gears. In its simplest form, a gear is a mechanical device which transfers rotating motion and power from one part of a machine to another. Gear sets transfer power through very small areas of mutual contact. Gears have evolved from primitive wooden wheels with wooden pins, as seen here in this Chinese south-pointing chariot. Built in about 2600 BC, it provided its operator with a direction finder. Once set, the small figurine, operated by a complex series of gears, always pointed south, regardless of the actual direction of travel. This type of gearing continued to be used, as shown by this example of a grist mill from about 1500 AD, with its pin and lantern gears, which seem rather primitive by today's standards. Even the complex involute tooth design, widely used on modern gears, was the subject of a mathematical study by a Frenchman, Philippe de la Hire, as far back as 1694. An involute curve, from which the gear tooth design derives its name, can be generated by a point on a taut string when it is unwrapped from a circle, or by a point on a straight edge that is rolled on a cylinder. The involute tooth combines rolling contact with sliding contact, beginning as the flank of the tooth on the driver meets the tip of the tooth on the driven gear, and progresses until contact between the tip of the tooth on the driver and the flank of the tooth on the driven gear ceases. A basic requirement of gears is the smooth transmission of loads. This is accomplished by maintaining a constant angular velocity ratio. Since an involute gear has no fixed pitch circle, the involute tooth profile permits two involute gears to transmit a constant velocity ratio at any distance between the centers of the shafts for which there is continuous contact. The opposing tooth surfaces of spur, helical, or bevel gears move over each other with a sequence of sliding, rolling, sliding motion. Pure rolling occurs only momentarily at the pitch line. Hypoid and worm gears have no pure rolling motion between the two gears. Traditionally, we view gears as wheels with cogs, or teeth, the basic spur gear, for example. But many applications, especially in automotive gearing, make use of annular or internal gears, because the arrangement is much more compact. Also, because the teeth travel more nearly in the same direction, there is less sliding action, which tends to increase the efficiency of power transmission. Notice that the tooth profiles of annular gears are concave, which increases the surface contact area, reducing the intensity of pressure and loading on gear teeth, which tends to decrease wear and increase the life of the gears. Some basic working terms encountered in gearing are shown in this diagram of a section of a typical spur gear set. The larger of the two gears is referred to simply as the gear, and the smaller of the two is known as the pinion. The top of the gear tooth is called the top land, while the upper portion of the meshing surface of the tooth is referred to as its face. The gear face, on the other hand, is actually the width of the gear. The pitch of a gear is a measure of the spacing of the teeth. In this diagram, we see that the size of the gear teeth increases as the circular pitch increases. Notice that the gear teeth do not extend to the bottom of the alternate space on the opposing gear. The depth of penetration is known as the working depth, while clearance between opposing gear teeth as they are meshed is known as backlash. In dealing with gears, an important term commonly used is gear ratio. This refers to the relationship of the number of teeth on the gear to the number of teeth on the pinion. In practical terms, it describes the ratio at which gears transmit speed or torque. At constant power, speed increases as torque is decreased, and vice versa. A gear train is simply a system of interconnected gears. Gear trains are used when the desired gear ratio is too great for two gears, and when the distance between shafts is not too great. They also come into play when constant velocity ratio is necessary or desirable, and usually when a large velocity reduction or mechanical advantage is desired. Planetary gearing is one example of a gear train, and gear sets that reduce output shaft speed, often called gear reducers, also fit the description. The simplest and one of the most widely used gear types is the basic spur gear. Easily identified by teeth formed parallel to the axis of rotation, these gears are used to transfer power from one shaft that is parallel to another. Because only one pair of teeth is in contact at any time, the load that spur gears can carry is limited. The popularity of this gear type comes from the fact that it is the most easily produced and therefore the least expensive to use. The durability of spur gears represents an added benefit. Spur gears may be either internal or external. A close relative of the spur gear is the helical gear. The difference between the two is that with spur gears, teeth are cut perpendicular to the axis of rotation, while with helical gears, teeth are cut at an angle to the axis of rotation. Not surprisingly, the angle formed between teeth and axis is called the helix angle. Because several teeth are always in contact along some portion of the tooth face at the same time, these gears tend to run more smoothly and quietly. It also means that they can carry greater loads, or torque. But because of the helical configuration, thrust loads are transmitted sideways along the axis of the gear shaft and must be handled by shaft bearings. Increasing the helix angle increases the face contact ratio. That is, provides more teeth in the contact zone, which distributes the load among more gear teeth, but also causes an increase in the thrust loading. To achieve the benefits of a helical gear and eliminate the thrust load problem, a variation of the helical gear known as a double helical or herringbone gear is employed. This configuration produces a thrust load from each helix equal in magnitude but opposite in direction, so that no net axial thrust load is imposed on the gear shaft. However, with this arrangement, one of the gears must be free to move axially with respect to the other to align the two helices and equalize the tooth loads on each helix. Otherwise, single helix loading will occur. Helical gears are used where smooth, quiet operation at high speed is required, because they provide for a more gradual shifting of load from one gear tooth to the next. Notice that helical gears may be used where shafts are parallel, but they may also be employed with intersecting shafts. In such an application, they are referred to as crossed helical or spiral bevel gears. Where shafts intersect at right angles, gears are beveled to fit like a mitered joint. Gear teeth may be either parallel to the axis of rotation, spur, or at an angle to the axis, helical, in which case the gear is referred to as a spiral bevel gear. Because of the gradual engagement of more than one tooth simultaneously, the spiral bevel gear is capable of greater loads and operates more quietly than an ordinary bevel gear, even at high speeds. The hypoid gear presents its own special case. Similar in appearance to spiral bevel gears, the distinguishing feature of the hypoid gear is the fact that the axes of the shafts supporting the gear and the pinion are in different planes. Hypoid gears are used extensively in the automotive industry because, with the pinion axis below the axis of the gear, the drive shaft may be lowered, providing either a vehicle with a lower profile or greater ground clearance. However, the very offset that produces the benefit also creates problems. Gear teeth are larger, and there is higher relative sliding velocities between contacting surfaces, presenting special lubrication requirements. Where heavy loads must be transmitted at relatively low speeds, or the required speed reduction between shafts is large, worm gears are used. Worms have helical screw-like threads wrapped around the worm axis. They may be considered an extreme case of a hypoid gear. Shafts are characteristically non-intersecting and at right angles. Worm shafts represent the maximum offset between shafts. Since the worm rotates like a screw, high sliding velocity is developed between contacting surfaces, and like hypoid gears, special lubrication requirements may be created. Since gearing is a complex subject, we will now review some of the elements of the different gears in the same order in which they've been presented. First, the spur gear, with teeth formed parallel to the axis of the shaft and operating on parallel shafts. Next come the helicals, with parallel shafts, but teeth cut on an angle with the shaft axis. The angle is known as the helix angle. Then we have double helical or herringbone gears, with helical teeth at opposing angles with the axis of the parallel shafts. Bevel gears, with shafts at right angles, employ teeth either cut parallel to the shaft axis or in the helical mode. In the latter case, they are called spiral bevel gears. Hypoid gears, used in automotive applications, operate on non-intersecting shafts, usually at right angles. They resemble bevel gears, but the gear teeth are of a special form and profile. Worm gear sets are identified by non-intersecting shafts operating at right angles and helical, screw-like teeth wrapped around the worm axis. Most gear applications are uncomplicated, with specific gear combinations designed to perform a limited function. Automotive gearing is another matter. Here, the complex is the norm. Hypoid gears predominate, but bevel gears, pinions, and ring gears all have a place in the complex matrix of motion that exists within the automotive environment. But most critical is the differential, which permits the wheels of a vehicle to turn at different speeds during cornering. Two side gears are employed, with each attached to the inner end of one of the two driving axle shafts, so they face each other. Two or more differential pinions are mounted on a solid cross shaft, or spider, if there are more than two differential gears supported by the differential case. These are meshed between the side gears. The driving ring gear is rigidly mounted on the differential case. Torque delivered to the differential by the spiral bevel or hypoid gears is transmitted through the differential spider and the differential pinions to the side gears and axle shafts. The pinions act as balance levers between the two side gears, dividing torque from the ring gear equally between the two driving wheels under normal conditions. When the two rear wheels are moving at the same speed, the differential pinions do not rotate about their axes, and the differential acts as a solid unit. A very important concept to remember is that the torque of each axle is always equal. Therefore, if one of the driving wheels slips for any reason, the torque of that axle is reduced to zero. But since torque on both axles must be equal, the torque on the other axle also becomes zero, and that wheel doesn't turn, even though it may have excellent traction. On the other hand, a limited slip differential permits the axle supplying power to the slipping wheel to transmit some of the driving force to the wheel with better traction, which permits a vehicle to operate even though one wheel has lost traction. From North America to South America, from Europe to Asia, from 2600 BC to today, from the south-pointing chariot to chariots of fire, we depend on gears, the hidden asset, to keep things moving.